Wires. The wires that you use to charge up your phone. On the outside, black plastic, bendy. On the inside, very thin copper wires. I have some copper here. This is much thicker copper. The copper inside the wires in your charger wires are much thinner, and that's why they're all bendy. The plastic, the black plastic, is there to stop you getting electric shocks. Don't do this. Underneath the black plastic, when you're thinking, oh, I don't need this wire anymore, it's broken, underneath the black plastic is copper. Thin little wires. Be careful. Make sure that it's unplugged and just about to be thrown away before you have a look at the copper. Definitely unplugged. No electric shock. The plastic is an insulator. It stops electricity going through it. Electricity can't get through the plastic. The electrons won't go through, but electrons can get through metals because metals already have lots of free electrons moving around, just hanging about, ready to be pushed along through the wires. Copper is a conductor of electricity. It conducts, just like a conductor on an old-fashioned bus, a bus conductor. Copper wires inside. The plug you put in the wall, the 3-pin plug they have in England, has got 3 different colours, so you can figure out which wire goes to which pin. The long pin that goes in first at the top, bigger, longer. That one has a wire going to it that's green and yellow. Green and yellow are the colours you get if you ask a primary student to draw the Earth. When they draw the Earth, they have the sun yellow, green grass. The green and yellow wire, it spirals around in a helix. The green goes around and the yellow also goes around. A little bit like DNA, but that's another lesson. The green and yellow wire is the Earth wire. That's the one that stops you getting electric shocks. Something goes wrong inside your fridge, or your washing machine, or your dryer, because fridges, washing machines and dryers are made of steel. They conduct the electricity. If something goes wrong inside, and one of the other wires is touching the inside metal, the whole fridge is ready to give you electric shock. Apart from the earth wire is there. Green and yellow earth wire, lovely earth wire, saves you. Because what the earth wire does is it connects to the inside of the fridge. So if there is a possibility of getting electric shock from your fridge because one of the other wires has gone rogue, then the electricity can go through the steel of the fridge, then straight down into the earth. An enormous burst of electricity for a millisecond goes through the 3-pin plug and gives you a burst of electricity that melts the fuse. So only for a millisecond is there a build-up of current and then the fuse melts. So if your fridge stops working, maybe it's because something's wrong inside the fridge and the fuse has melted. And so therefore, you can find out if it's really the fridge that's the problem by putting a new fuse in. Take a 13 amp fuse out, put a 13 amp fuse in. You can buy them at the hardware stores. The fuse is there to melt. You can't see anything melted unless you break inside the fuse. It's to melt to save you from electric shocks. Put a new one in. If the fridge still doesn't work, then something's wrong with the fridge and you need to buy a new fridge. If you put a new one in and the fridge starts again and it's working, then maybe it was a power surge from the power station and everything will be all right for a few years now. In England, you get a power surge maybe once every 10 years, a decade. In Manila, in the Philippines, once every 10 days. You have to buy a new fuse. But it's a lot cheaper than buying a new fridge every 10 days. So fuses are good. They save you a lot of money. They only cost 10p or 50 cents American. 10 cents American? Yeah. There are two other wires. The first one to the long one, the one at the top of the 3-pin plug that you push into the socket, into the wall, the one at the top has got the earth wire. You want the earth wire, green and yellow, to be colours of the earth, yellow sun, green earth. You want the earth wire in before the dangerous wires go in. The dangerous wire that's brown is called the live wire, because brown is the colour of brown bacteria in dog poo. Don't eat the dog poo. It's dangerous. And so is the wire that's brown. And on the brown wire, you've got attached a tiny little fuse. And so when the power station, which is 25 miles away from your house, when the power station pushes electrons to your house through the brown wire, if the fuse has melted because of something going wrong, then the electricity can't get into your machines towards you. So you'll be safe. The other wire that can give you an electric shock, though, is the blue wire. Blue is the colour of water. And water, when you do chemistry, water is pH 7, neutral. So the blue wire is called the neutral wire. pH 7 is neutral. Acids, alkalis, neutral. The neutral water, blue wire, it's blue. Copper inside, just like the brown wire has got copper inside, but the plastic outside is blue. Or the plastic outside is brown. Or the plastic outside is yellow and green. So the plastic colour tells you what their jobs are. The brown wire lets electricity come from the power station to your phone. The blue wire takes it back to the power station. The power station is a huge big wheel, a turbine turning with magnets, making enormous amounts of electricity to give thousands of people the electricity they need in their homes, to charge their phones up, and less important things like make the lights work and the cookers and your television. All of the things, your Hoover, that are electrical in your home, work with this system. I have others. Also in your home will be these. This one's not connected. There'll be a box underneath the stairs in your kitchen, a big metal box, maybe plastic. And if all of the lights go out, or all of the plugs stop working, and you go to this box. Or maybe it's the fridge, the freezer, and the cooker stop working. You go into the box, you open the door. You can spend £100, get an electrician to do this. But they've made it much safer nowadays because of the circuit breakers. In the past, you needed a wire and some knowledge, and there was chance of dying through electric shock, but not anymore. So when you get there, there'll be these little clicky switches, and one or more of them will be down and red. And all you do is you click it back to green, and suddenly all the lights will work again. You've just saved yourself £100. I'll let your dad do this until you own the house yourself, because your dad might be getting unhappy. Other electricity things. Batteries. Inside your remote control is a battery. Using AA or AAA batteries, they say 1.5 volts. Pause the video, go and have a look inside. Although, don't lose those batteries. Inside the remote control, there's a clicky bit on the back. They say 1.5 volts. They might say Duracell or some other brand. I've got a peak power here, but this one says 9 volts. These ones are for experiments in physics schools. schools that do physics. This one's good, even though it's inside its wrapper, because you can get electric shock from it. It's only 9 volts, whereas the voltage in your house is 230 volts. Or you might say 210, or 220, or 240, or 250. It's a lot of volts. Enough volts to push the electricity around your whole house. It needs a lot of push, a lot of volts to go a lot of distance. The remote control, it only has to go 10 centimetres around the wires, the copper wires inside the remote control, and of course the brains of the remote control, the little computer inside, that makes infrared radiation. If you point it at the camera, your remote control, point it at your camera on your phone, you see it buzz up. Your eyes can't detect infrared, but your phone camera can, usually. Anyway, 9-volt battery, good experiment to do with this, although you're probably not allowed to do them anymore. Used to do, 20 years ago when I started teaching physics, you can put a tongue on it and then get yourself electric shock in the tongue. It never killed anybody, but nobody likes getting an electric shock, it hurts. Next one I want to show you. The ammeter and the voltmeter. So in a school, you get ammeters, voltmeters like this. Now I said the volts enough to push the electricity around your remote control. You've got 2 1.5 volts batteries. Really they should be called cells, and 2 of them is a battery of cells, just like battery chickens and battery and artillery. Battery means many. You've got 2 1.5 volts in your remote control for your TV, and they add up to giving you 3 volts. And 3 volts is enough to go the few centimetres, maybe 10 centimetres, around the remote control. Whereas to go around the whole house, you need 210, 220, 230, 240, 250. It will say underneath your kettle and underneath or at the back of your toaster. Pause the video. Go and have a look now. It will say 210 to 250 volts. Because they're plugged into the mains. They use mains electricity to plug into the wall. For school, we do a voltmeter like this. So, you put, in school we use black and red wires, just like the black and red wires in the walls that bring the electricity to your plugs, sockets. The electricity goes from the breakers through the wall down to the socket, which means drilling holes in walls can be dangerous. You can get electric shocks that way, and you can suddenly turn off all the electricity. Be careful where you drill holes. You can get machines to check, see whether there's a wire behind the wall where you're just about to drill. Voltmeters. The wires in the walls are black and red. So in physics we use black and red. So here it says 3 volts, and here it says 12 volts. And this voltmeter is still in its packet. We haven't used it yet. So it's called full-scale deflection. And where it says 12 volts, if you plug it in there and black, those 2 plugs, then can you see it says 12 at the top? So when the pointy bit, you see the red one, when that pointer is pointing there, you have all the way across here would be plus 12 volts, all the way across here would be minus 12 volts going in the opposite direction, the electrons. At the moment, of course, it's reading 0, which is none. If you use black and 3 volts, then you're not using the top scale, you're using the bottom scale at full scale deflection. So it would go all the way over here to 3 volts and all the way over here to minus 3 volts. So where it says 4 for the top, it says 1 underneath. Voltmeter. Not used in the home, only for teaching electricity. Ammeter. Oh, hold on. Voltmeter. Voltmeter has inside it a huge resistance. So the huge resistance says to the electricity, are you pushy enough? Have you got enough push to come through me? That's why, if you've got a circuit, that's the symbol we use. For a cell, 2, 3 or more, and you've got a battery of cells. This bit here, any thin line, means it's a wire. Circle with a cross. It's an indicator bulb that we use in science. We also use it for light bulb. 2 circles on a line, switch. Switch closed. Switch open. I'll close it again. Switch closed. Okay, if I now want to find the volts that's going through this bulb, then I have to connect the voltmeter to this side, the black wire, and to this side, the red wire, and it's drawn like this. V for voltmeter. So I have 2 wires coming out of my voltmeter. Voltmeter. 1 to each side of the light bulb. That will tell me how many volts of push are going through this light bulb. Well, seeing as I've got 2 batteries, that's 2 1.5s. 3 volts. This voltmeter will read 3 volts. Be careful of 3 volts. That's actually enough to heat up the thin metal filament, metal wire, inside the light bulb. It will heat up so bright, it will melt, and you've just wrecked one of my light bulbs. So I'm going to change that. Okay, here we go. Okay, right. I've just, right, okay, that's better. Now I've only got 1 cell. 1 cell, 1.5 volts. My little lamps in my circuits apparatus in physics, they can take 1.5 volts. Okay, and the voltmeter will read 1.5. Capital V, after the Frenchman called Voltaire. Yeah, we named volts after him. America uses 110 volts. So if you buy something from America and plug it in England or anywhere else in Europe or the world, it will go and then stop working. You need a transformer to transform the electricity so that it can be used if you buy it in America and you want to use it in England, or the other way around. You need a transformer. Okay, so now I'm going to use the ammeter. Ammeter counts how many electrons per second, the amps, named after Mr. Ampere. So I could put the ammeter here, or here, or here, or here, or there. Okay, anywhere that all the electrons have to go through, I can put my ammeter. I can put it there or there. The ammeter has to be in series with the light bulb. All of those ammeters will read the same. 1 milliamp. 1 milliamp. 1 milliamp. 1 milliamp. 1 milliamp. 1 milliamp. Milli means it's 1,000th of an amp. Yeah. It's the volts that jolts, it's the mils that kills. Watch the amps. Definitely don't want a whole amp going through you. That's a deader. But I don't need to lie this many ammeters. 1, 2, 3, 4, 5. All of those ammeters are in the right place. They're in series. The voltmeter is in parallel because of parallel lines. 1, 2 parallel lines. Can you see that one? I'll draw it higher. Okay, get rid of that. Parallel lines, mathematics. So this line is parallel to that line. They're called parallel. In science, we don't draw the arrows. Only in mathematics do we draw the arrows. I don't need 5 ammeters. I'm going to get rid of all the rest and just keep that one there. So all of those places to put an ammeter are correct, but you only need 1 to get the reading from the cell. Now I've got the amps. Now I've got the volts. I can use V equals IR. V equals IR. Mr. Ohm OHM. You figured this one out.
So voltmeter at 1.5 volts, 1 milliamp times R.
Okay, I'm going to rub things out and leave the equation on board. Here we go. Okay, my ammeter in series, my voltmeter in parallel, gone, gone. And this is milliamps, just like millimeters. There's 1,000 milliamps in a whole amp, so I have to put 1,000th here.
1/1000 amps times by R equals 1.5 volts.
Move the equation around.
Equals 0.1
divided by 1,000. Stop the video, put that in your calculator, press equals.
001 amps, 1.5 volts times by R.
The opposite of times is divide.
So that gives me R equals 1.5 volts divided by 0.001 amps.
Okay, that's going to give me
1,500 ohms.
Yeah. That's quite a lot of resistance. Because it's a very thin wire. Cool. My ammeter also has a black for the electricity all to come through. All the electricity goes through an ammeter when it counts the electrons. It has to count all of them. Voltmeter measures push. How much push can you push through this voltmeter with all the resistance inside, making it difficult to push through? Ammeter, no resistance at all. Just come through. I'm just going to count you. So you can see the red needle at the top. It's on 0. And there are 3 full-scale deflections this time. One of them says 0.5 and one of them says 1. But there are still 3. Because if we look carefully, focus, there's the possibility of going 1 amp. There's the possibility of going 0.5 amps, and there's the possibility of going 0.5 milliamps. See the M? Cool. So if you've got it in the black and the 1 amp, all the way to full-scale deflection, there would be the 1 amp. Or plus 1 amp, minus 1 amp. If it's on the 0.5 that it says there, can you see the decimal point? So if you've plugged it in black and 0.5 amps, all the way across here, you wouldn't be measuring the top numbers, you're using the bottom. Plus 0.5, minus 0.5 amps. But if you put it in the black and the milliamp socket, all the way across here would be plus 0.5 milliamps, all the way across here, minus 0.5 milliamps. Full-scale deflection. This ammeter measures different amounts. You can measure milliamps or whole amps. And that's just the science amps. The science apparatus. Really, if you're fixing cars, or doing jobs in a house, or you're an electrician, you get one of these. They're actually nowadays cheaper than buying the ammeters and voltmeters I use for my lessons. This is a multimeter. You click it around, you plug it in. You have to read the instructions. It takes a little while. Get your dad to show you if he's got one. You plug it in, you click it around, it will tell you how many amps, how many volts, how many ohms, how many hertz. Hertz! Hertz is how many times the power station is going round. The power station turbine turns around. So, how to make electricity? You heat up water. You heat up water either using uranium, and you have a nuclear power station, or coal, you have a coal-fired power station, or gas or oil. You heat up water and the water goes up because steam rises. Have a look at your kettle sometime. When the kettle boils, steam goes up. Steam rises because cold air is pulled down, hot air like hot air balloons, go up. This is called convection. It's to do with gravity pulling cold, dense, squashed together molecules like cold air down and letting the ones that are less pulled by gravity, the expanded, hot, whizzing around, fast, moving, taking a bigger volume, air molecules, they go up, cold ones go down. Heat rises. And, oh yeah, big wheel of magnets. Hold on, difficult to see. Use blue. Big wheel of magnets. That's better. Big wheel of magnets turning round. In Europe, it turns around 50 times per second. This is called 50 hertz. 50 times a second, big wheel turning around. Whiz. It's whizzing around because hot water, steam, H2O gas, steam rises, pushing the turbine, turning the turbine. Cool. All the magnets are going. They push electrons to your house for 1/50th of a second and then pull electrons from your house for the next 50th of a second. Always through the live wire. Pushing the electrons through the live wire to your house. And then the electrons exit your house via the blue wire. Or pulling the electrons from your house and the electrons get sucked in via the blue wire. Continuing, the other way you can do turbines is if you have a turbine spinning because of water power. Water going down a mountain. You've put a dam across the river and the turbine goes round as the water goes wishing past. Or, apart from hydroelectric, dam-made electricity, you can also have wind turbines. They spin round like windmills. When the wind blows, you get electricity. Whole bunch of magnets turning around. In America, it's not 50 hertz 50 times a second. It's 60 hertz. 60 times per second. That's one of the reasons why you need a transformer. If you buy it in America, plug it in Europe or England. And 110 volts. I believe this was because their science was a little bit off, and they thought lower voltage, lower push, less likely chance of getting electric shocks. Yes! But it's the volts that jolts, the mils that kills. If you have less volts, you need more milliamps, more chance of being dead when the shock hits you. We use, in the UK, 50 hertz, 210 to 250 volts. It doesn't matter which, just as long as it's enough volts to push it around your whole house. So, any machine that says 210, 220, 230, 240, 250 will work in your house. So that's cool. Oh, you can't see the V for the volts. Now you can. So that's cool. Yeah, because of V equals IR, if you halve the voltage, which in America they do, this doubles the current. And power equals IV. Again, if you halve the voltage, you double the current. And it's the milliamps that kills. The place you'd find really large voltage is in the pylons. Pylons look like the Eiffel Tower, and they carry wires that bring the electricity to your house. And these have to have enormous amounts of voltage to push it to 25 miles from the power station to your house. And that's why you don't go climbing up these, because
if you climb up these, and they have got 100,000 volts,
which is about right for a pylon hanging in the air, bringing the electricity to your house.
if you climb up this Eiffel Tower to about there, and
Don't actually touch it.
you will get a bolt of lightning like electricity come and hit you in the hand, and you fried.
Be careful out there. Lightning. Lightning is electricity. High voltage electricity. Sometimes you survive a lightning. One man who worked in the Rocky Mountains National Park, he got hit by lightning 5 times. The first 4 times, no problem. The 5th time, he got so unhappy. He didn't die, not from the electric shock. But it all made him so unhappy. Yeah, he shot himself. Electricity from lightning. Benjamin Franklin said, if you have lightning coming down to the earth, it's electricity. He said, I have proved this
by putting a kite in the air,
flying it during a thunderstorm. Very dangerous. Because the wire, the cotton wire in this case,
was wet, the electricity could come down from the kite, and he said it went to a key, and he said he could see the little lightning sparks coming off onto his hand. Cool. And he said he was inside a house at the time.
Several problems with this. Number 1, fly a kite, then climb in through the window, and then direct the kite from inside the window so you don't get wet inside your house. No way. Second thing, amount of electricity coming down here from the sky. It would hurt real bad.
Lightning has between 1 million and 100 million volts.
Needs this amount of volts to push the electricity miles through air. But it's the males that kills. And 1 in 5 electron amounts of amps going down from lightning or from your kite. Very inadvisably, don't fly a kite in a thunderstorm. Nasty, nasty, nasty. Really hurts. And 1/5 of the time, just dead. 1/5 of the time, there is enough electrons flowing down this wet rope. You're a gunner. 4/5 of the time, ouchie, ouchie, just hurts. Talking about hurts, America, 60 hertz. Ha ha! UK 50.
So what should you do when it's a storm and there's lightning?
Some people say,
Sit underneath the tree.
12 students did this in India.
The lightning hit the tree, and unfortunately all the students X'd. It's very important to know what to do in trees.
In storms, don't go underneath the tree.
Don't stand up.
Do not play golf. Do not hold an umbrella. Golf clubs, umbrellas, made of metal. Not always, but mostly. Many golf players get deaded by
Lightning. And also,
umbrellas are metal. In the Rocky Mountains, when I was there and the storm started, I got a little tingle of electricity coming down, wanting to make a line. Because when you take very slow-mo pictures, you see the electricity builds up from the earth and goes to the sky, and then the bolt comes down from the sky and hits the earth. Both happen from the earth up, from the sky down. Both. Don't play golf. Don't use umbrellas in a thunderstorm. What should you do if you're in a field?
well, the thing you should do is just crouch by the ground
With your raincoat over you. and wait until the storm goes by. Definitely don't go swimming, because lightning hits swimming pools too, and the sea, and if the lightning hits, it spreads out. And that's what happened to the Indian students. Tree got hit, tree wet, lightning went down into the ground, and then through all the students, through their hearts, through their brains, stopped them working. Be safe out there. The reason why I teach physics is so that you guys can invent the iPhone 96. And also so you're going to be safe. And you'll know your electricity. This is Mr. Science Stevens. Be careful.